Good morning, good evening, or good afternoon, everyone, depending on where in the world you are. My name is Jan Brugod. I'm the CEO of Wolfram MathCore and leading the development of System Modeler. I'm here today to basically just to present the presenter, Vedat Chenol, who will talk about the rotating machinery library. But before I hand over to him, I thought I just give a brief introduction to System Modeler, as some of you might be new to the tool. So I thought I'd give you, as said, a quick introduction to System Modeler and what it's all about. So System Modeler is a drag and drop environment where you can create models of all sorts of dynamic systems. This could be a biochemical pathway, it could be a business system, or as in this case, a DC motor. So it's a sort of school book example of DC motor that we're looking at. In the middle here, we have an electrical system, we have a mechanical system, a 1D rotational system in this case, and then that's connected with a control system that tries to keep it at some desired operation point. And the idea with it is that you as a user typically should just have access to these components and be able to use ready-made examples, modify them, or start from scratch and build up your own. The way you would do that is add something from all these built-in libraries that are available and drag, drop it to the canvas. Like here, I added a torque step. I will connect it somewhere. Let's say that I put it on the outgoing shaft here. And I would parameterize this to say, for instance, what's the torque I will apply? Let's say I apply a negative torque of 1 Newton meter. And perhaps I want an offset. In this case, I don't want an offset torque. And I want it to start at some time. So let's say that I started after, what do I know, 12 seconds, like that. So that's the way you would be building a model, and then you would simulate it. Here we actually have a pre-run that I ran just before. So now we're getting the update, and we could see the difference. You notice that suddenly everything changed from this point on, and that was because I added this torque. I applied that, and apparently the system or the shaft is so weak that it starts to oscillate when we apply this, and it doesn't manage to control the system well. At least if we look here at the first part of shaft, the blue, it sort of looks good. At the end part, it's oscillating a lot. So that's the whole idea with the product. You have these components, you build your system, and you start to simulate and see what happens if I do this, what happens if I do that. Will the system work well? Will it not? And if I head back to, hopefully, there you go. If I head back to the modeling environment before I leave the word over to Vedat, just to indicate here that in this particular small example that we started with, there is actually a gear, a small, simple gearbox. In this case, it's an idealized gearbox. So that's one of the features of the tool, that you can have ideal simplified things, but you can also have components that are super detailed and advanced, and combine them depending on your need. What Vedat will be showing today is on the side of really detailed and advanced, and you will see that while he is presenting. So with that, I leave the word to you, Vedat. Thank you.
Thanks, Jan. This morning, it is likely that you use everyday items like a bicycle, a car, or even electric toothbrush, making that familiar tiny buzzing sound. And do you know what these items have in common? They all use bearings, and these essential components help countless machines with rotating parts operate smoothly. In fact, SKF, a leading bearing manufacturer from Sweden, reports that people around the globe require more than 330 billion bearings every year. Hi everyone, my name is Vedat. I work as an applications engineer at WolframU and have a PhD in structural control. For the last 3 years, I have been using System Modeler extensively to help with different consultancy projects and to contribute to developing new libraries. And today, I will talk about our latest project, the newly released Rotating Machinery Library. As an engineer who contribute to its development, I will guide you through its key features. Then, we will explore how this rotating machinery library can help you and go over some of its relevant details. Right, let's get started. In our journey through the world of bearings, we encounter various challenges that can affect their performance and the lifespan. Understanding these issues is crucial to prevent downtime and ensure machinery operates at its peak. And we have different type of problems. Firstly, we have clearance issues. This refers to space between the moving parts within a bearing. Incorrect clearance can lead to premature wear or even failure. Roller can jump around. Then we have misalignment, which happens when the inner and outer rings are not perfectly aligned. This can also cause uneven wear and potentially damaging stress on the bearing. Contamination is another challenge. Even the smallest particles can cause significant damage by creating abrasive wear and changing the bearing's integrity. And well-known problem, vibrations, and often imperceptible. And this vibration can also have profound effect, leading to noise, wear, and eventual failure, if not properly managed. Lastly, we have excessive loads, and these loads surpass the bearing's design capacity, resulting in overheating and deformation and even breakdown. And all these factors reminds us that proper selection of bearing, handling, and maintenance are essential. We will explore how to address these challenges with a detailed example later in this presentation using rotating machinery. Okay, as we shift our focus to another key component in rotating machinery, let's talk about gears. These critical pieces adjust the torque and the speed to transfer power effectively within machinery. Imagine gears in bicycle that help you go faster or apply less effort when pedaling. Similarly, these intricate components in machines adjust the power to suit different operational needs. However, gears face their own set of challenges. Backlash, for instance, is the play between the teeth when changing direction. And then we have again vibrations, which can arise from imperfections in gear teeth, leading to noise and damage. And here also we have the misalignment, and misalignment of gears can cause uneven wear and even premature failure. And last but not least, we have excessive loads. Just like with bearings, excessive load can lead to overheating and deformation of the gear. And interestingly, a comprehensive study of over 1500 gear failure instances revealed that the predominant issue was tooth bending impact. This type of failure illustrates the importance of understanding the forces at play and ensuring that gears are designed and maintained with these stresses in mind. As we delve deeper, uh, we will look at real-world examples and strategies to prevent failures and ensuring longevity and efficiency in our machinery. Right, challenge with real-world system. In the realm of engineering, Bringing concept into reality is an iterative process, especially when refining boundary conditions from connected components. Take this offshore wind turbine as an example. Engineers must often extract foundation and hub forces through separate simulations at the device level, and then apply them to neighboring components. While this type of analysis is invaluable, it typically relies on the predefined boundary conditions and may not fully account for dynamic environmental interactions. So, it is the iteration in this process that underscores the importance of system level modeling because this process takes so much time. Such an integrated analysis framework enables engineers to simulate dynamic interaction within a rotating machinery, capturing the interplay among, for instance, controllers, motors, and bearings. And this holistic approach is essential for developing mechanically robust systems. Systems that are not only designed to withstand physical demands, but also are fine-tuned for conceptual and mid-level design phases, as well as operational stability. Now, we consider the types of problems we face: a complex interaction between all components and subcomponents. Each part's performance can significantly influence the entire system. It is a symphony of engineering, where each instrument must be in tune. This is another challenge that we can take on with rotating machinery. Okay, the first example, bearing example. As we delve into our engineering symphony, let's focus on a system that vividly illustrates bearing challenges. Here, we have a featured machinery with two Timken 313 AG bearings. One with a defect, a key issue we need to examine. And this setup also includes a load applied shaft, which split into two and runs on a controlled power source. So let's consider the type of problems we might encounter in this type of machinery, like clearance. Clearance is essential in our system. We adjust the clearance on the bearings, which can sometimes be negative, reflecting no space between the moving parts and leading to more robust machinery under the applied loads. Because whenever the rollers get up, if there is no defect and they don't counter the loads applied, misalignment may seem minor, but is a tough one. Even a minimal shift in the bearing alignment can lead to a significant wear and system inefficiency. Brinelling and contamination are prime suspects for the defect in our bearing. Brinelling can leave permanent marks on the roller outer cage and due to the excessive force, and while the contamination can get into the bearing, damaging the inside, unseen but not unfelt. And of course, we have vibrations, which are often tied to this defect, signifying deeper issues and amplifying the risk, particularly if machinery speed approaches to the critical speed, like the whirling frequencies. And we have, of course, excessive loads, challenges us to check the stresses on the roller to discern if an overloading force has been applied and pick a bearing size for optimal performance. The presence of defective bearing in this model, whether due to the brinelling or contamination, can set off a chain reaction, leading to vibrations and set off complication. Just as in an orchestra where one of tune instrument can affect the entire performance. In machinery, a single fault of bearing can throw the entire system out of sync. So our objective, to detect, analyze, and correct these imperfections to ensure smooth and harmonious operation. Right, in this simulation, we are examining the forces on the roller bearings, where one of the bearings has been introduced with a zero point 0.1 micrometer defect. And this defect translates an approximate impact of 500 newtons. You can check our documentations to calculate the corresponding defect from the defect size in force from the defect size. For ease and clarity in our model, we represent this defect through a force equivalent method, which simplifies the integration into the system dynamics. So you can imagine that you might have let's look at the blue line here, which shows the roller forces in defective bearing. And we have the regular bearing depicted in orange. Our bearings are preloaded, which is why our simulations begin with constant force. So, and this practice ensures that, as we talk about, the rollers are always under compression and they don't move around freely between the outer and inner cage. For the regular bearing, the force applied by outer cage fluctuates periodically with the roller's rotation, increasing as the roller descends and decreasing as it approaches the 12 o'clock. The defective bearing exhibits the similar pattern, but with additional peaks due to the defect. And these peaks correspond to the roller position relative to the defect. When the roller encounters the defect, we see the maximum force impact, illustrating a significant load. Understanding these force patterns is essential for predicting bearing behavior under defect conditions, which ultimately helps in refining our designs and preventing failures in real-world applications. Let's take a closer look at the bearing forces. Right, in this plot, we are looking at a stark visualization of bearing roller forces applied by the outer cage over full 360 degree angular range from minus 180 to plus 180 degrees. So notice how these forces of regular bearings behave in expected pattern, right? Increasing when the rollers get between the load and outer cage and decreases as they move away. So here at this position they increase in amplitude, and at this position they decrease in amplitude because in that part when they rotate 90 degrees they move away, they get to the top. Now let's turn to the defective bearing. At first look, it follows the similar pattern, yet we can't miss the ripples, the peaks over here, and these signify the extra forces introduced by the defect. The defect located inside outer cage, positioned at 12 o'clock, we witness an increase in force as the roller approaches the defect and decrease as it continues towards 6 o'clock. So this is what we see. The peak force on the roller occurs at plus 90 degrees, right over there where we hit the defect. And this is the point of close approach to the defect under load, right? As the roller progresses in its rotation, we see the minimum value right after this defect, which is around, in this case, like plus 96 degrees angle. As we mentioned before, the defect was introduced as a force. It was 500 newtons. If we get the defect force back, this amplitude, we could get a symmetric pattern in defective bearings. It would look like that type of peak, and we would end up having symmetrical pattern even in defective bears. Okay, let's have a look at the dynamic animation. The red arrow here marks the defect position on the outer cage, and it is always at the 0 degree angle. That is how we position that. As each roller shown in blue, over there, we are looking at blue, transits over this defect, and there is a sharp increase whenever we goes over the defect. So observe how the first roller, initially at like at 270 degrees over here, moves towards the defect, and the peak force occurs as the roller reaches 90 degree angular displacement directly over the defect, and continuing its position. If we will see that now, it will be coming again. So here we are almost there. So right before and after this, like this position, minimum and maximum, and again we observe the minimum force applied to the roller, the first roller. So, and by looking at this animation, we see the roller forces, and such bearing simulations, I will say, are invaluable, allowing us to predict, plan for the forces within our bearings, and to understand how clearance, defects, and system dynamics contribute to overall bearing load profile. Okay, so And now we have gearbox example. Right. When we turn our attention from the inner workings of bearings to the gearbox of a wind turbine, a component that often encounters issues due to the unpredictable wind force. And the early breakdown of gearbox can lead to significant operation halts and the financial loss. Fortunately, we can anticipate and address these challenges through advanced simulations using rotating machinery. And we will now examine the Acciona AW100/3000 gearbox, a key player in wind turbine operation. Identified here is item number 5. Right, it is a complex assembly featuring a planetary gear and 3-stage gearbox. So this is the gearbox we are looking at inside this Acciona, and this is how we model that gearbox using rotating machinery. A planetary gear, a 3-stage gearbox, and one shaft in between. So while modeling that, we use pre-configured components from the rotating machinery to accurately model the gearbox, and the critical specifications like gear size, teeth count, and the gear alignment are easily configured by entering precise values in our model. Right, we simulate the model starting with a ramp-up speed profile for the propeller, reflecting the real-world conditions. Now, let's turn our attention to animation before us, and this animation brings to the life to the planetary gear and 3-stage gearbox and connected through a single shaft coming out from the sun wheel attached to the first wheel inside a 3-stage gearbox as we modeled in the rotating machinery. So the forces I am going to show are located at this point and this point. So now the contact point between the one of the planet wheel and the sun wheel, the point I show, and the contact between the first and the second wheel in the 3-stage gearbox, the second point I show. So has the largest contact pressures. I just plot them. I choose these points on purpose because they show the high contact pressure when I look at the simulation results. So when we look at the stress plot for these two contact pairs, we are comparing the stress on the gears to the allowable stress limit for ASI 5161 steel. And this is the material the Acciona use in the Acciona turbine gears, at least one of them. So this steel has an allowable stress limit of like 1800 megapascal. Notice that the peak contact stresses are higher in the planetary gear. Despite this, they stay within the safe limit. When we look at this figure, we also observe that there are zero contact forces, like there, meaning that either another teeth pair in contact or there is a backlash. However, this might be not the whole picture, because there are so many dynamics to capture on these forces, right? For instance, why we have this type of jittery stress profile when two teeth in contact. Is it because of the interplay of the other teeth, and why this is taking longer than the others? So we need to answer those questions. And in the figure before us, we observe the contact pressure at a key location within our gearbox system over a specific time interval, the places I show on the animation. The top graph focuses on the planetary gear, where we notice a slower rotation, right, which takes longer time, and the lower graph, which represents the 3-stage gearbox, which rotates at higher speed, and that is why in a given time we see more contact. And at this point we notice that there is no contact either in the front pair or the back or the rear pair, which might be caused by backlash. And also you see we have so many vibrations, so many dynamics to capture here. And it is also well known that these vibrations can lead to gear failure, marking it as an area of concern. Right. And finally, real-world system. Expanding upon our gearbox analysis, we now progress to a holistic model, a real-world example, or system, let's say. This is not just gears and shafts, it's an entire wind turbine. And now we see that we already have the gearbox we already used, which represent that one, with additional bearings, a shaft in between the propeller and the gearbox, and a propeller and a tower. I checked the Acciona AW100 3000 wind turbine system and found out that 100 refers to its hub height, which is 100 meter. So I modeled that thing using the flexible beam component from our rotating machinery library. And now we have everything in place. And also remember the challenges we discussed. Here is where they come into play on a grand scale, right? This comprehensive model allow us to examine the dynamic responses of the turbine, responses influenced by the backlash, vibrations, misalignment, even excessive load we intended to identify earlier. It is crucial to address these issues to enhance the durability and efficiency of wind turbine. And in this model, we get a step closer to understanding how every component from top of the blades to the base of the tower plays its part in this symphony of engineering that is wind power generation. On the other hand, as we inspect the system, we remind that every part, no matter how small, contributes to turbine's overall performance. And this intricate interaction of the components demands our attention to prevent failure and to optimize functionality, ensuring that our renewable energy source stands the test of the time and the nature. So let's look at the animation of this holistic system looks like. In the animation, we have the opportunity to watch the rotation of each gear inside the gearbox. To keep our focus clear, I just left out the tower. And as we observe here, the gears transition, the slow turning of the blades. So it is slowing, distinguish, to catch. Yeah, here it is. The gears transition the slow turning of the blades into much higher speeds needed at the outgoing shaft. This is the heart of our wind turbine's energy conversion. Now we arrive at a critical question. Do these additional components, the system level modeling, pose a risk to our system by pushing contact stresses too close to the allowable limit? The plot before us over here makes this comparison evident. So the contact pressure from the gearbox on the model, the one we already checked before, the orange one, and the blue one shows the holistic model. And in both cases, we only plot the planetary gear stresses, contact stresses, and not the three-stage gearbox, because we observe the maximum limit there, the maximum stresses there. Just a glance is enough to tell us that the contact pressures are now getting closer to the allowable stress limit with the 1700 megapascal. Still, despite this, our simulations indicate that we are fortunately still within the safe boundaries. However, we see that the dynamics change at initial drastically. So we see that the peak we reached before with the gearbox only model takes longer to reach, and also gaps over there takes longer. So all these differences should be investigated truly to understand whether these differences, these dynamic cause any dangerous consequences. Even though our analysis here stays within limits, it underscores the importance of meticulous attention to detail, particularly when considering the entirety of systems dynamics. And this is precisely the strength of the rotating machinery library, coupled with System Modeler. In our exploration today, we have seen firsthand the power of the rotating machinery library. And we can use the rotating machinery to, like we did over here, model complex components such as motors, generators, and turbines with precision. And we can use it to dive into the details, examining the inner workings of each part, from teeth of a gear to rollers of bearing. And also we can use it to understand the complete system, considering how each element interacts within the greater machinery. Right, I guess we are pretty much done. As we wrap up, I encourage you to think of the intricate system you encounter or work with. How can the lessons from today's session enhance your approach?
We had a couple of questions in the Q&A that where people were a bit confused whether the animations you were showing were from another tool or how that worked. So can you talk a bit about that and show
And
how it actually is in the tool?
yeah, sure, Jan. All the animations are generated using System Modeler. Right, here we are looking at our gearbox model, which we modeled using rotating machinery. And we have our gearbox planetary gear, and we run the simulation, which I already run. We will get this simulation center with the results. And when we run it, here we have the animations. When we click that, all these animations comes with rotating machinery. You can have it. Now we see that our rotating machinery. Here we have the gearbox, the planetary gear, and also we have three-stage gearbox. And you might think that you might wonder what these forces are. I just amplify those to see better. That's why then they look ridiculous now.
So let me stop you there. So you say these forces, but with these forces you mean these arrows, the blue and red arrows.
Right, you are
So
right.
so what what
Right.
what what are they actually showing?
So now these forces, when we look at here, those are showing the contact forces between the gears. Whenever we have a gear mesh, let's pause it over here, for instance, we see that not all over the places, on the teeth are in contact. We can see these forces. So while designing a gearbox, this is essential thing because there is no any stress here.
Uh,
The max
yeah. So good. Is so and then I assume you can turn these on and off. You don't have to see them all because now it's like a lot of forces, right? So can you control that
right?
in some
Yeah,
way?
yeah, yeah. We can control that. We can just uh, choose the animation off, and
Right.
then
Okay.
they won't be shown. And you
Perfect.
can also scale them.
Right.
So you can make these arrow smaller.
Mm.
Uh, yeah,
Yeah, because otherwise, depending on the scale, they show you can see the relative magnitude between the different forces at the moment. I guess.
right, right.
And what's the difference between red and blue arrow in this case?
Red and blue. One is the rear, the other one is front contact.
Great. And can I then see, because this just shows, so can I see the some plots that gives more precision to it than this, or what kind of data do I get from it?
Right. So we can have a look at the contact forces, for instance, here. Okay, click that. Hopefully, yeah. For instance, now we are looking at the. Let's look at this one first. Right. These are the citruses we are looking at now. We can either look at citruses or even forces. So all is possible, but looking at the citruses at this level, it is more beneficial compared to looking at the forces because just by judging the citruses you have, you can say that okay, uh, this gear material, this design, at least is within the allowable limit and won't cause any damage even if I run this dynamic simulations.
Right.
We
Okay. So
can
so so can you also show, yes, that what have to zoom in a bit to see what sort of details do you get here?
right. So for instance, we can just look at the. I will do that if my computer permits. I have so many things running on now. Okay. So here we see that how this forces responding to increasing RPM. So because we have the blade speed, which is ramping up to 20 RPM, starting from zero. So there is no any additional like in Newton terms force in this system, in this machinery. All the forces created here because of this propeller speed, and the computation of these forces takes into account the contact hertz theory and responds the frequency characteristic of the load as well. So depending on that, we see what type of stress we develop. Also, we can check the indentations, how much, let's say, deflection we have in teeth.
Right.
So
So,
that
so,
that is
so es essentially what you're saying is you can dive into any particular detail you're interested in. You can dive in, start analyzing, and then of course you can start doing analysis either right here in this tool or do it in the Wolfram language to understand more of
right,
the system. Is what you're saying. We
exactly.
we we have another. We have a few other questions on the animation. So I want to just take the opportunity to answer those. So there is a question whether we can use whether there's built-in graphics in it, whether you can use things from System Modeler Mathematica tools and add. And I can answer that. So basically, the software itself now, the rotating machinery library has predefined shapes and so on, and is what you're seeing right now. So that you don't need to do anything. You drag and drop your system together, you simulate, and this will be available. But if you want to do something that has a specific CAD shape, then you can do that, and you can use Mathematica to import a CAD shape and then uh, import that further to System Modeler. So you can use that to have something fancier if you want that. So basically, with the animations, you have both built in, but you have also the possibility to adapt this as you want. Uh,
Right, right. Also related to gear geometries, what you need to do, just set the parameter here, like a gear module and what is the width of the gear and etc. And when you set all the parameters, you will get this automated cat shape in your
uh,
simulation.
yeah, so they will adapt there, and that's so. If we go back to the modeling part, um, now we mostly saw things ready-made and stencil. So let's say, for instance, that I would like to have a gear from SKF, a specific
Uh,
gear from SKF. How would I do
Bearing,
that?
you meant.
Yeah, a
Bearing.
bearing from SKF. Yes, sorry.
Right, right. So, right, in rotating machinery, we have the rolling bearings components, and over there, if you collapse this, expand this, you will notice that we have,
Can you
uh,
zoom in a bit on the at least on the
right,
items?
yeah, yeah, that will
It's
be even
very
better.
very small.
You're right. So here it is. Okay, maybe we can open documentations. So you see, we have
And
the
again, the zoom for most people this would be very small.
right. We have already pre-configured like leading manufacturers in the industry related to the rolling bearing. If you are planning to model an SKF bearing, then you can just click here and you will get this documentation how to model your
Can you make this full
corresponding.
screen and bigger so people actually see what's going on?
Right.
Uh, keep increasing, keep increasing, and
And
now I
now,
think most people will be able to see it.
right. So you ask for like SKF, and here, if you have specific bearing, let's say any model, you can name it. So for instance, that's one, the one marked with red. You can read the corresponding parameters here and go to the model All the we are showing how to read corresponding
How to
parameters.
read them? Yeah, right.
Yeah, and related to like radial internal clearance and how many roller it has and etc. We have all the links. You can just click and go to manufacturer, the supplier website
So
to get this catalog
basically,
as
yeah,
well.
basically what you're saying that you're supplying a recipe. So from manufacturer data, you can just put those data directly in as parameters in the model, and then you have that
Right.
bearing configured, is what you're saying.
Right, that is what I
Yeah,
say. So here,
yeah.
for instance, we have the SKF and we see
Okay.
the corresponding parameters to set over there. Now I will just make try to show this part. So you see we have the bearing dimensions over there. So the parameters you need to set are this. So you will go to catalog, you will go to documentation and figure out how to read this parameter from the manufacturer. After reading those, you will register, you will set those parameters to get your specific bearing. And then you will get your custom bearing.
Thank
And
you.
if
Thank you.
if you don't have any bearings in between among them, we have five of them to show. You can just follow the same workarounds and found the catalogs and the parameters and register that.
Okay, thank you. So there are plenty of other questions.
Should I
There was
stop sharing?
no continue sharing.
Okay.
You probably have you are the guy having the answers.
So,
Um, let's see here which one I was. Yes, so there's a question here whether there are moment of inertia in the gears. So does
right.
is that taken
Yeah,
into
yeah.
account?
Yeah, that is taken into account. When you set all the parameters, it is calculated automatically.
Great. And are there which other are the most important things you would say that are taken into account that people you think people would be interested in having there?
In general or related
In
to gears?
general, for the in the rotating machinery library.
Right. In the rotating machinery, I will strongly recommend checking the example package because here I will show that. So because in this package we listed categorized different type of analysis like bearing analysis we did like defect related forces investigation, and other than that we have like a stability analysis in which you can just do probably some of them you might heard the Campbell diagram, which is about the stability of the rotating shafts and checking the forward whirling and backward whirling. And uh, these are pretty uh, useful analysis while assuming that like you are running a machinery and then you just change your mind for some reason and decide to run the machinery at different speed. But before doing that, you need to be sure about whether you are crossing the whirling frequency. So I guess simulating this is cheaper than the testing in real life. You can come and check whether the machinery survives in that new frequency, new rotational speed. Other than that, we talk about the gears. What else I can say? For instance, like
So yeah, so I think that's enough for it. There's plenty of questions, so we're trying to keep the answers to the point, and then we dive more into if we get follow-up questions. I think that's good.
okay, yeah, yeah,
So there was another question here on an overview how the load from the generator sending power to the electrical grid is simulated, and I guess that's partly how it's actually modeled, and then what happens with it.
Oh, in this model, we haven't done anything about in that related to that part, but
But in
eventually,
general, so pick up
in general,
pick up an example here that actually has that, because you showed that during the presentation, right?
in the
So
presentation,
you had an example of the wind turbine that actually had a,
right, we
yeah,
have this wind turbine over there. Maybe we can talk about over that.
yeah.
So let me make this bigger. So we have the mechanical aspects of this gearbox over here. We have a blade which is rotating at some certain speed, and eventually we elevate its rotating speed, rotational speed using this gearbox. And then here we have a faster rotational speed which goes to the
Right,
generator.
but in this actual example, you haven't included the generator.
Right, I haven't
But
included the
of course,
generator.
if I take the answer then to this, so yes, there are libraries. Can see there are many ways, of course, to model the generator, and you can connect this just as the other elements. Just as I added the torque in my beginning first example, you could take a generator from the built-in libraries or build your own and then connect it to here to see the actual effect of that. Or if you would like to add the control system and so on, that's also things that you could add.
Right.
Uh,
So here there might be two approaches. Either you just connect a sensor here to measure the rotational speed, and depending on that, you can come up with your generator. And or as Jan rightly said, you can have a causal component and connect that thing to this system, and then you will have a system which also interact with this generator. If the generator shows some resistance to the movement, then that resistance will be included in this model as well.
so does system use the latest Modelica version, which is the latest version? So there's the latest version of the Modelica language, and there's the latest version of the Modelica standard library. And we are on the latest on both the language and on the library. And as for the library, that means 4.0. I should sort of remember this.
Right.
Perhaps you remember. Yeah, it says there what's the number is
Yeah, for
4.01.
4.00, that is
Zero
what
zero,
we have.
yes. So
Right.
so that's the latest. There is a new version coming up soon. It's not yet finalized, but as soon as that comes up, we will release with that. So yes, we're on the latest version of both the language and the library. Okay, right. So and this is for you, Vedat. I think it's a quick answer. I see now the wind turbine model looked at the bearing roller loads on the inner and outer cages, not the shaft torques. Good enough answer, yes. But you can explore. So basically, you can choose to plot the torques and a bunch of different things. So what kind of things would you be able, if you want to extract from these simulations?
Right. We had a, I mean, for the post-processing
Yeah, in
purposes.
general, yes. So if you would
Uh,
like, can you plot torques? Can you plot forces? Can you
uh,
plot
right. Yeah,
what
yeah, yeah. Right.
distances?
Whatever.
What kind of things can you actually get from the simulations?
Right. So this library is also compatible with the multibody, Modelica multibody library. So related to any 6 degree of freedom, like a force, and then the torque, and then the angles, and then the linear force, you can get all those values. You can plot those.
And assume positions, speeds,
Right.
and so on,
Yeah,
right?
position speeds.
exactly.
right? Um, and then if there's something that is not included in the library that you specifically want to do, you can actually add either in the model, add things yourself to them
Right.
to calculate extra things, but or you can do that in the post processing using the results, create expressions that calculate that. Um,
And
right.
even if you think
Yeah,
something useful we are missing, then please let us know, and
yeah.
we appreciate the feedback, and we might implement it as well.
Perhaps that's a good way to wrap up, Vedat. If you could show where they can find the rotating machinery library if they want to download it. And then here there are different ways of finding system model. One of them is to, oh, they have updated the page, but you click on products
Right.
and services on top. That's always the easiest way to find it. And
Here we
you'll
have the
find
system
system
modeler.
modeler.
When we get here, we have the libraries. And inside the libraries, we have a rotating machinery and the others like aircraft
Right.
and business simulation and so on.
Good. So from there you can find the rotating machinery library, download it. But as you saw, there was also other libraries, and for all of them will look similar to this. So you see here that there's a short description of it, but there's also links to examples how to use it and how it works and so
Right.
on. So there's plenty of resources. Uh, and for the you that asked about business simulation examples, if you go to the libraries here and click on business simulation, afterwards you will actually easily find several examples on business related stuff.
Like product chain.
Yeah.